Our next speaker is Professor Osama Hoho from the University of Media in Algeria, who will be talking about universal quantum computation with mechanical oscillators. Yes, Professor Osama.
Thank you very much and welcome to everyone. First, I would like to thank the organizers of this first Moroccan Quantum Day for organizing this very nice talks, and also for inviting me to give a talk in this very nice event. Also, I'm very glad to see events like this having such international aspect, both in the region and in Africa. And I hope this event will be of great success this year and also for the next years. Also, I'm sure that these events will be a good opportunity for future collaborations between quantum scientists in the region and in Africa in general. Again, thank you for this very nice events, and I wish all the best for the organizers and also for the participants.
Thank you so much, Professor Osama.
Okay, so I will share my screen. Okay. Yes. Do you see my screen now?
Yeah.
That's good. Okay. So my talk today will be about universal quantum computation with mechanical oscillators. So in this talk, I will be talking about quantum computation using the vibrational degrees of freedom for movable objects. My talk will be outlined as the following. So first, I will talk about the motivation of this work. Why am I interested in studying quantum computation using mechanical oscillators? And then I will be giving a very short and brief description of open quantum dynamics. Namely, I will be talking about steady states, and from that I will talk about, or I will introduce you with the notion of non-Gaussian cluster states. So how to prepare them using open system dynamics. Then I will give a optomechanical implementation of the system of my model that I will be talking about. And from that, I will talk about how can we do Gaussian measurements, how can we measure arbitrary quadratures of the mechanical oscillators in an optomechanical setup. And the point before the last one is universal quantum computation. How can we use non-Gaussian cluster states with the addition of Gaussian measurements, and how can we use them to do universal quantum computation? And in the end, I will conclude my talks. So first, what is quantum computation? So in short, quantum computation is the processing of information using the laws of quantum mechanics. So you see here in the slide, let's imagine a quantum computer like a black box where it accepts input data and modify or process this data using the laws of quantum mechanics and produces a new data. I will call it the output data or the results of the computation. In quantum computation, the input data or even the output data, so data in general, is encoded in the state of a quantum system. And we can differentiate between two types of quantum systems. The first is discrete systems, where they are described by a finite Hilbert, finite dimensional Hilbert space, while on the other hand, the continuous systems are described by infinite dimensional Hilbert spaces. And in this talk, I will be focusing on this later type of systems. So quantum computation using or in continuous systems or continuous variable systems can be done in many different ways. One of the ways is the so-called measurement-based quantum computation. In this model, a resource state, so the input data that I was telling you here, so the resource state is the state of a given system, is a very special state that is a highly squeezed and entangled state. And we measure specific nodes of this state in a given order in order to modify the state and to do computation and get the output of the computation like you see here. So this is the one-way model of quantum computation, or the measurement-based quantum computation. And my work, or before that, the quantum computation, in quantum computation, we speak about universality, meaning that can we do any computation given an input state and do any or arbitrary computation on it. So there are two approaches to reach universality. One of them is you need to have a resource state that is Gaussian, and you need to do both Gaussian and non-Gaussian measurements on it. So when I say a Gaussian state, what I mean by that is a state that can be obtained by a unitary transformation generated by a Hamiltonian that is at most quadratic in field operators. So this is the first approach. Again, a Gaussian cluster state, and you need to do Gaussian and non-Gaussian measurements. What I mean by Gaussian and non-Gaussian measurements, so measurements that can, operations that allows you to measure field operators or field quadratures, and also higher orders of these field quadratures. So the square of these fields, or the cubic order of these fields, and so on. So this is the first approach. The other approach is let's say, the transpose of the first one, meaning that we only need Gaussian measurements on my cluster, but on the other hand, I need to have a non-Gaussian cluster state. So in this approach, we need to first prepare a non-Gaussian cluster state that can be obtained by a generating Hamiltonian that is more than quadratic in field operators. So what are the advantages of one approach compared to the other? Regarding the first approach, so yes, the first approach, it needs a Gaussian cluster state. That's good, that's easy, relatively easy. But the hard or difficult part of it is implementing non-Gaussian measurements. While in the second approach, it's easy to implement Gaussian measurements in experiments. And here in this talk, I will be showing you how to prepare this non-Gaussian cluster state. Okay, so my work involves two stages. First stage is the preparation of the non-Gaussian cluster state. And after that, the second stage is doing measurements on this cluster state in order to do quantum computation. So in first stage, I will introduce you about I will introduce you with the notion of non-Gaussian cluster state. So in very short words, a non-Gaussian cluster state is obtained by applying first I squeeze individually many modes in vacuum state, as you can see here. So I squeeze each mode individually, and then I apply what is known as the cubic phase gate, and this is generated by a cubic Hamiltonian, Hamiltonian in position, for instance. So squeezing, then applying the cubic phase gate on each mode, and after that I apply a coupling or entangling operation, for instance the controlled phase gate, which is shown here. And how will I reach or generate this state is by using reservoir engineering techniques. So I will consider an open system, and then by engineering the coupling of this system with its environment, I will show how to reach the target non-Gaussian cluster states as the steady state of the system. So this is in general how will I do the first phase of the protocol. The second protocol is consuming this resource state. In other words, doing computation, and this is done via measuring arbitrary quadratures of the phase of the field. And again, I will be doing this in a dissipative manner, meaning I will be using reservoir engineering again. Okay, so let me talk about open quantum systems in a brief. Here I will be considering a system consisting of two subsystems, subsystem A and subsystem B. In a given interaction picture, let us assume that the total Hamiltonian of the system is given by this Hamiltonian. So you see, this Hamiltonian is something like a beam splitter-like interaction between system A and system B, where A is the annihilation operator living in system A, and F is some collective operator or a field operator living in subsystem B. Let's forget at the moment about this expression of the field F. If the system is closed, meaning there is no interaction between the total system and its environment, so I will get or we will have a conservation of the total quanta of the system, and this is shown here. Say that we start with 10 quanta in the system, and because this is a beam splitter-like interaction, there will be a transfer of quanta between system A and system B, and you can see that this dynamics is periodic. Again, this is a closed system. The other situation and the more realistic situation is when we consider interaction between parts of the system or the whole system with a reservoir. For the dynamics of the system state is described by a master equation. Let's assume that this master equation has this form. So here the field operator A is dumped to the vacuum with rate kappa. So for kappa different from 0, we have, as I said, a open quantum system, and now the quanta number of the quanta count of the system is no more conserved quantity, and it will decrease by time. If we allow much enough time for our system, there will be no quanta present in both system B and A, and this is clear from this curve. As you see, at the long time limit, both A and F of system A and B are in their vacuum state. Now, when I say vacuum state for A, this is the ket 0, the vacuum here. And when I say the vacuum for F in system B, I mean some ket phi that satisfies this dark state condition. So F phi equals 0. This is the meaning of a vacuum for a given operator. Okay. So my object here is to set or fix a target state, and let's say that our target state is the cluster state, the squeeze state, the cubic phase gate, any state that you want to prepare. So if you want to so we have two situations. If F, this collective or this field that is living in the B subsystem, is canonical, meaning that I can obtain it by applying a unitary transformation to the annihilation operators living in system B. So we can demonstrate very easily that the steady state will be vacuum, or this unitary applied to the vacuum. On the other hand, if F is non-canonical, okay, there is nothing to prohibit us to consider a non-canonical F, but the price that we will pay is that the steady state is not always guaranteed to exist. And if it exists, one has to solve this dark state condition. For the people from the audience that are interested in how to solve this dark state condition and obtain different kinds of states, they can consult this paper. Okay, here I will give just two examples. So the first example is, let's say that we have only one mode, and I want to squeeze that mode. I squeeze the state, so I obtain a squeezed vacuum state. We know the squeezing operation is given by this formula, where S is some squeezing parameter. If I calculate U, B, U dagger using this expression here, I can find what are the couplings G1, G2, G3, G4, G5 that will allow me to prepare the squeezed state. And we can find that we need to put G3, G4, G5 equal to 0, and G1 equal S plus 1 over S, and G2 equal S minus 1 over S. And if I let my system to reach its steady state, I'm sure that the steady state will be the squeezed state. On top of this, if I want to prepare the so-called cubic phase gate, sorry, the cubic phase state, I need to turn on the couplings G3, G4, G5 and set them equal to 3s gamma over square root of 8. And in this way, I'm preparing the cubic phase state, which is this operation applied to the vacuum. So this is just a very short introduction how to reach a target state as a steady state of a system. Let me talk about Gaussian or non-Gaussian cluster states and how can we generate or prepare them using reservoir engineering. Again, let me remind you what is a non-Gaussian cluster state. So a non-Gaussian cluster state is obtained by squeezing every vacuum mode and then apply the cubic phase gate, and then we entangle different pairs of modes according to the adjacency matrix A. Okay, so the U that I was talking about before is given by this the application of these three operators. So squeezing, cubic phase gate, and then entangling, or the controlled phase gate. My approach is a n-step preparation protocol. If you are interested in details about this switching or n-step preparation protocol, you can check this paper. So this n-step preparation protocol is as following. So first, we find what are the couplings, the G1, G2, G3, G4, G5 for each mode. So you see there is an index superscript J here denoting or describing different modes. So what are the couplings of the different modes that after n-step preparation, as I will talk about, will give me the target non-Gaussian cluster state, this one. So what I will do is the following. First, I look for or search for these couplings by solving this equation. So U, I apply the unitary U on the annihilation operator of the kth mode, and then find those couplings. Now, the Hamiltonian will take this formula, and again, this is a beam splitter like Hamiltonian. If I let the operator A the decay to the to vacuum, what I will get after a long time and the system reaches its steady state, I will get a given steady state. We don't care about what is the steady state at this moment. What we do next is switch the values of the couplings such that the new couplings will be obtained by the unitary transformation of the annihilation operator of the next mode. And we repeat this protocol. So switch and wait for the steady state, switch the couplings and wait for the steady state until I reach the last step. The last step, the steady state of the last step, will be my non-Gaussian cluster state. And this is how I prepare my resource state for computation. This is phase one. As an example, the two-mode non-Gaussian cluster state is obtained by the following. First step, I set my couplings. So I have this Hamiltonian you see here. I let the system reach the steady state. And this is clear from here, from the fidelity plot with time. So here, the fidelity doesn't change. So my system reached its steady state in the first step. I switch again to next step. So I have new couplings, as you can see here, and then I let my system to reach its steady state again. So this, you see here, the steady state at the second step has fidelity 1, and this means that yes, I have reached my target two-mode non-Gaussian cluster state. Okay, now let me talk about optomechanical implementation of such system. Here, I consider a cavity, an optical cavity, and inside this cavity, let us say that we have an membrane, semi-reflective membranes inside it. So there will be an interaction or a coupling between the cavity field and the vibrational movement of the mechanical oscillators here. And in addition, I will pump this cavity with a classical multi-tone laser field. So let me just go quickly to the Hamiltonian of the system. So the system consists of cavity. So this is the Hamiltonian of the cavity, and the n mechanical modes. This is the Hamiltonian of the harmonic oscillators, the mechanical harmonic oscillators. And here, these two terms describe the pumping by the laser. As I said, there will be a coupling between the field, the cavity of the optical field, and also with the mechanical vibration of the membranes. So the Hamiltonian will show some optomechanical interaction as shown here. So we have a cavity Hamiltonian, mechanical Hamiltonians, and here I have a optomechanical interaction. As you can see, I have stopped on the second order the Taylor expansion of the frequency, the modulated frequency. And I need this in order to implement the Hamiltonian, the beam splitter-like Hamiltonian that we talked about it before. Okay, so this is the core of the protocol. To each mechanical oscillator, I associate 5 laser driving fields. So the first, so 2 lasers address the first sidebands, the red and blue sidebands. Another 2 laser field address the second sidebands, and 1 laser will address or will be resonant with the cavity. And so I can show that this Hamiltonian can be written in an interaction picture with a rotating wave approximation as this Hamiltonian. Again, here you see that we have the beam splitter-like interaction Hamiltonian. So we have the cavity field, and this is the collective field operator, the F, as you can see here. So this is my F. Okay, now I will talk about how can we implement Gaussian measurements on the cluster state using the optomechanical setup. Again, the same setup, but instead of considering 5 different lasers per mechanical oscillator, I will switch off 3 lasers and keep only 2 lasers that address the red and blue first side bands for each mechanical oscillator. And for time reasons, I will tell you that I can turn this Hamiltonian, this optomechanical Hamiltonian, into this in Hamiltonian, which is position interaction between the cavity and the different mechanical modes. And so this is the first step. This is the Hamiltonian. How do we implement measurements, Gaussian measurements, is by continuously monitoring the output field from the optical cavity. By doing so, we are implementing a new Hamiltonian that is also position and momentum interaction between the intracavity and the output cavity field. And because the cavity is also coupled to the x phi, the mechanical quadrature, we can show that by continuously monitoring the output field and waiting for a long time to reach the steady state, the state of the mechanical oscillator is projected to an eigenstate of x phi. So if the state is projected to the x phi, this means that we had done a measurement of x phi, since now the state of the mechanical mode is an eigenstate of x phi. So this way we can do any Gaussian measurement of mechanical field quadratures. So now I am in a position to talk about universal quantum computation, since we have our non-Gaussian cluster state, and we can do quantum Gaussian measurements. So here we have, for example, two-mode cluster state that is non-Gaussian. You see there is a cubic phase state here. By measuring the first mode by using the protocol I have talked about before, so by measuring the first mode, the other mode, the second mode, will be projected into a cubic phase gate applied to the input state here, modulo some Gaussian operations. So, and there is a famous and very known result that in order to do universal quantum computation, you need to implement arbitrary Gaussian operations. This is first. And second, you need to implement at least one non-Gaussian operation. And here we are implementing the cubic phase gate as seen here. So cubic phase gate applied to our input state. And by this, I conclude my talk. So in my talk, I have introduced you with a scheme to deterministically prepare Gaussian and non-Gaussian states. And in particular, I showed you how to prepare non-Gaussian cluster state. And also I showed you how to do Gaussian measurements on your different nodes of your cluster state. And by these two ingredients, we are in principle able to do universal quantum computation, and in particular we can do it using optomechanical systems and also electromechanical or all optical systems, given that you can implement a beam splitter like interaction between two parts of the system. And before I finish, I have to give credits to my collaborators, and also for the interested audience about details of these protocols, the preparation protocol and the measurement protocol. They are welcome to check my previous works about this subject. And yes, thank you very much for your listening. And yes.
Okay, thank you, Mr. Osama, for your presentation. You can also share your your credentials in the chat for people who are interested in contacting you, or for further information. That would be
Yes, sure.
great too. Okay.
Yeah.
Thank you.
Thank you.
For the audience, if you have any question, please don't hesitate to leave your question in the chat so Mr. Usama can give you some answers. Okay, here is a question from Professor Murad. Thank you, Usama. Great talk. Can the quantization of the laser field be included in your formalism? And have you estimated the impact of AWE approximation on the final results?
Sorry, say the second part of the question, please.
Oh, the second part is, have you estimated the impact of the RWA approximation on the final results?
Okay, thanks, Professor Murad. Yes, we can consider a quantized pumping field. So, but actually, I didn't consider, or I didn't study this case. I was interested in something that can be experimentally feasible using current technology. So I considered a classical field, classical pump, and using the phase of the classical pump and also the amplitude of the different tones in this classical field, I can tune or switch on and off the couplings that I was mentioning before in order to do this multi-step or multi-stage preparation of my non-Gaussian cluster states. But yes, in principle, you can apply a quantized field, but you probably you will not get directly using this scheme this exactly target state, but you can, or you may obtain other non-Gaussian target states that are in principle sufficient to do universal quantum computation. What I have shown here is only how to do the minimal situation. So we have a Gaussian measurement and a non-Gaussian cluster state. The minimal non-Gaussian cluster state is a cluster state that has a cubic element somewhere there in its nodes. And regarding the second question, what are the only approximations that I have considered are actually two approximations. The first is the linearization approximation. So I have linearized my fields around around their equilibrium values. This is the first approximation. The second approximation that I have used is sorry. So the second approximation, yes, is the rotating wave approximation, and I use this in order to get rid of the time dependence in my Hamiltonian as usual. Yes, in fact, in a realistic setting, the counter-rotating terms will contribute and will affect my target state. And I have addressed this in my paper. So those papers that I was showing you, one of them, and I mentioned there what are the let's say the conditions required in order to have your target cluster state with high enough fidelity. I hope that I have answered your questions.
Okay, perfect. Thanks, Mr. Usama. Another question from Abdelkader Makuri. Thanks for this nice presentation. Please, could you explain the meaning of the coefficient K in the master equation?
Yes, sure. Let me share my screen with you again. Yeah. Okay. Yes. So you are talking about, yes, this equation. So this kappa here describes, in a very short words, describes the coupling between subsystem A and its reservoir. So kappa is the rate of losing quanta from our system towards the environment. So I hope this will answer your question.
Okay, perfect. Okay, I don't see any more questions. So thank you again, Mr. Osama, and for the presentation and for your answers. That was perfect. And